This is worksheet 2.7. We're working on composite functions. So here we're trying to evaluate the function g when x is 7. And so here are our two functions that make up the composite function. Now this top one we only use when x is less than or equal to 7. X is less than or equal to 3. Whereas the bottom one we use when x is greater than 3. Then we can plug x in here to this equation and figure out what y is, or what the function value is. So for this first one we want g of 7. So we want to use the green equation, the bottom one, because that's when x is greater than 3 and 7 is greater than 3. So I'm just going to write the generic equation down, and now I'm going to plug in 7 for x. You don't actually have to do that top line, just showing which equation I'm using. So this function has a value of 13 when x is 7. And we could plot the point 7, 13. X is 7, y is 13. Now when x is 0, then we're going to have to use the top equation because 0 is less than or equal to 3. So g of 0 is going to be 0 plus 5, which equals 5. So when x is 0, y is 5. Probably actually don't have to write that coordinate pair down. I'm just stating that that's our x and that's our y. Again, now when x is negative 1, we use the top equation. So we plug negative 1 in for x. So when x is negative 1, we get 4 for y. Last but not least, now when g is 3, that would be this one right here, because x is 3 in our problem, and this top equation we use when x is less than or equal to 3. To use the bottom one, our value has to be better than or bigger than 3. So top equation, 3 plus 5 is 8. So when x is 3, y is 8. G of 3 equals 8. Sweetness! Alrighty, let's try graphing some of these things. Whoa. Whoa. Oh no. Graph the following functions. So we have two, I don't like this view actually. So this top equation works when x is less than or equal to 0. And this bottom one works when x is greater than 0. Some people find it helpful to take your pencil or something that you can erase and just kind of make so this is not actually part of my function, folks. This is not part of my answer. But I realized that when x equals 0, there's an interchange between the two functions. And so maybe it helps just to kind of make like a dashed line at x equals 0, a super dashed line, just to show that that's where the break in the yellow and the blue function parts are going to be. So when we're to the left of the dashed red line, that's when x is less than or equal to 0, we're going to use this equation where x is y equals x plus 3. And for that equation, our y-intercept is 3, and our slope is 1. So y-intercept at 3. By the way, this function works at 0. So when I make my y-intercept, which is right where the transition happens, it's going to be a closed dot because this function works when x equals 0. Otherwise, it'd be an open dot. And then a slope of 1. So you could go up 1, right 1, up 1, right 1, and down 1, left 1, down 1, left 1, down 1, left 1. But recall, it's just to the left of this transition line that this function actually works. So these 3 red dots that I made right there aren't actually part of my graph. Then once x is bigger than 0, the slope is 2 and the y-intercept is 0, right? So now I'm going to put an open dot at the y-intercept. I'm graphing the line y equals 2x plus 0. but I'm realizing I only actually color in, or I shouldn't say color in, I only keep the part that goes to the right of my transition line. So now I'm going up 2, right 1, up 2, right 1, and I'm not going to even bother going down to left 1 in this case because it would take me over to where the function doesn't work, or it's not part of the composite. Alrighty, so that was probably kind of weird. Hang in there. These are tough. I know. So now we have, for number 6, we have a new equation, new composite equation. So we're going to use this equation when x is less than or equal to 2, and we use the bottom equation when x is greater than 2. Oops, over here at number 5, I forgot to erase my transition line. The transition line now happens when x equals 2. That's when we switch between the two equations. So I'm going to make a dashed line, super dashed, at x equals 2. All right, let's graph the green line first. So the slope is 3 and the y-intercept is positive 1. So down 3, right 1. Y-intercept is 1. So y-intercept is positive 1. Going down 3, right 1. Down 3, right 1. Up 3, left 1. Up 3, left 1. And I could keep on going. I could keep on going to the right as well, but realize that this function only works when x is less than or equal to 2, which means to the left of my transition line. Then, let's graph the other line. So when x is greater than 2, so to the right of this transition line, y equals 4, right? Because isn't that the same as y equals 4? Which would be if it's y equals, it's a horizontal line at 4. Now, when x actually is 2, we use the green function. So maybe I'll connect it with the green line. Whoa, that's not a very straight line. Anyway, this function even, the green line even counts when x equals 2. Well, even when we get to right here. Now this function only works after 2. So that's why I kept this an open dot. When x is 2, we use this one. That's the y value, not there. So then from here, again, our height is 4, or y equals 4, but only to the right of the transition line. There we go. All right, 2 more. We can graph these. These are going well. So now I have 2 different equations, and it looks like the transition line happens right when x is negative 1. So I'm going to make a transition line. That's not actually a math term, by the way, folks, but I think it helps us see where the 2 lines meet for our composite function. So for this line, the y-intercept is 1, and the slope is down to right 1. Are you using a pencil? Good, I'm glad. So the y-intercept is 1. We're going down 2, right 1, down 2, right 1, down 2, right 1, up 2, left 1, up 2, left 1. Let's lightly make a line. Whoa, wow. Now this function only works when x is less than negative 1, which is to the left. So I'm going to now take my eraser, because I'm using a pencil, right? And you have an eraser too? Good. I'm going to use my eraser and erase everything to the right of the transition line. And then I'm going to question, hey, do I actually make a closed dot right, come on, Bessie, right here or not? Well, this function isn't actually part of the composite graph when x is less than negative 1. It does work. The green function works when x is negative 1. So I want to open dot here because this part's not included in my answer. Open dot, open, when x is negative 1 for that function. This one will be closed. So now I'm going to graph this other equation with a y-intercept of 0 and a slope of 3/5, up 3, right 5, up 3, right 5. I should have done this in a different color. And then you're going to also go down 3 and left 5. Down 3, left 5. So then This one is filled in because this line is part of the function when x equals -1. So there we are. Let's clean this up. Let's get rid of this arrow that I was talking about before. Let's get rid of our transition line. Maybe you made it so light that Mr. P is not going to be confused and wondering what you were doing. All right, there we go. So now let's try number 8. So number 8, this probably kind of bothers some people. You could rewrite it as y equals 3, right? And then our other function is going to be y equals -x plus 3. Y equals -x plus 3 when x is greater than 0. And then y equals 3 when x is less than 0. What's funny here is, what about when x equals 0? You know what? That point doesn't exist on our graph. That's okay. So, transition line, if you're into making that, happens when x equals 0, because that's where we switch from one line to the other one. This first line is y equals 3. That is a horizontal line. And I'm going to do an open dot. Boom. And to the left. When x is less than 3 is to the left. Whereas to the right, we're going to use this function. So the y-intercept is +3. But I am making an open dot there, folks. Hey, that's right there. But it's also still an open dot. And then our slope is -1. So down 1, right 1. Down 1, right 1, etc., etc. Zing your line. Forever and ever to the right, we'll be using this blue line. Bada bing, bada boom. Alrighty. Last two. Write equations for each piecewise function whose graph is shown. So here, if we go backwards, we talk about a transition line. My transition line is when x equals -2. Now the line to the left is when x is less than -2, and notice it has a closed-in dot, so it's less than or equal to. Whereas the other function is when x is greater than, but not equal to, because it's open, -2. All right, so now we need to write an equation of this line. I'm going to keep on moving it up there. If it were to keep on going, it would intersect right there. So this line has a y-intercept of 2. Remember, we're thinking slope-intercept form here, essentially. I'm going to write it down here. We're thinking slope-intercept form, so y equals mx plus b. For this line, it's a y-intercept of 2, and that slope is +1. So y equals x plus 2. But now instead of y equals, we're going to do f of x equals x plus 2. F of x equals x plus 2 when x is less than or equal to -2. And for the other line, let's do the same thing. The y-intercept is at, we'll change colors now. For this line, the y-intercept is at -3. So y equals some mx plus b, the b is -3. The slope is up 1, right 2, up 1, right 2. So 1/2 x plus -3 or -3. So let's go x over 2, which is the same as 1/2 x minus 3. There we go. If it helps, just like, if you're not sure, especially if this is a test, like, go backwards. Does this give me the blue line? Does this give me the red and black line? Oops, although I don't know, we're not graphing, so it's okay however you mark this up. This is the answer right here. When I graph this black line, does it give me the situation? I think that's really good. Nice. All right, number 10. Where does our transition happen? When x is 3. So f of x equals, well, one equation when x is, oh, that's funny, when x is 3. Now this one is when x is less than or equal to 3. And this one is when x is greater than or equal to 3. So technically this is